molecular interaction. And you, Tsunoda, from Chiba University. So I would like to talk about special matrices called X-codes. X-codes are used in integrated circuit testing for data compression. Integrated circuit testing is checks whether the circuit is correctly manufactured according to the design intention. To do this, the tester applies test pattern to the manufactured circuit and monitors its response and declares the circuit is defective if its output is different from the tester's prediction. In short, we want to detect the discrepancy between observed and correct responses. The first problem are due to the large volume of input and output data and long testing time. Therefore, various cost reduction techniques have been studied, such as automatic test pattern generation, response compaction. We focus on the techniques of the latter kind. The idea is that by using a well-designed compactor, we compress the responses in a way discrepancies still appear the compressed version of observed and correct responses. This way, we only need to compare a small amount of data. If you are familiar with group testing, indeed, this is essentially the same as non-adaptive group testing for example, DNA. A major issue peculiar to compaction for circuit testing is the fact that the correct output data to be compressed may contain some unknown logic value. But unknown logic value arises mainly due to the growing number of components and extreme complexity of modern circuits. To overcome this uncertainty, we use X-code as a compactor in the test. X-code have 4 parameters, T and D and X. A T and D X-code is a T times N binary matrix and that ensures up to D discrepancies between observed and correct responses can be detected even if up to X bits are unknowable by comparing the shrunk responses MA and MB. A is the observed response and B is the correct response. N is T and D X. The definition of the X-code is this. This is natural generalization of well-known combinatorial structures such as carbon-free family distance matrices and survival code. When D is equal to 1, the definition of TN1X X-code is the definition of TN1X X-code coincides with that of X X disjunct matrix C. A TNDXX code hashes n bit output into T bit. From the circuit and the test. The code word is a common vector of X code, and length of code word is the number of rows. So, the weight of code word C is the number of ones in C. This is an example of 9, 12, 1 to X code. So, because D is equal to 1 and X is equal to 2, the Boolean sum of any two columns does not cover any other column. For example, the Boolean sum of these two columns is this. And the Boolean sum of the vector is does not cover first, second, third, and or other columns. Here is an example of 4611X code. When the observed output is 0, 0, 0, 0, 0, 0, and the correct output is 1, 0, 0, 0, X, by using this 4611X with M, MA and M, the Planck responses and the observed response is 0, 0, 0, 0, and the Planck response of the correct response is X10X. The discrepancy between A and B can be detected by comparing A and B. And this output is shrunk into T bit. So we want a TNDXX code with large compaction ratio n over T. So we want a matrix with the smallest number T of rows for given T NDX. Let L of NDX be the length of code word of a TNDXX code, such that no T prime NDXX code has code word of shorter length. Here is the tightest known lower bound on L of N1X. Because by definition, a TNDXX code is also a TN1XX code. So this is the lower bound on L of NDX. On the other hand, this theorem 2 is the tightest known upper bounds on the length of code word of a general TNDXX code. The proof is essentially a simple counting argument, and it can be expressed as simple closed form like this without losing tightness too much. To improve the norm bound, we employed a slightly more sophisticated probabilistic argument and obtained this theorem. This is clearly tighter than the norm bound. The norm bound is exponential in x, and our bound is quadratic in x. For comparison, here are some numerical exam calculation. Figure 1 shows when n is equal to 3,600 and d is equal to 6. The vertical axis shows the length of code of X code by each cell, and the horizontal axis shows the number of unknown logic values, X. This purple dot line is known upper bound, and black dot line is known lower bound. And this blue line is new upper bound. And the length of forward, the smaller length is better because we want shrunk small. So the exponential improvement by our bound can be seen in this figure. Now we are coming to the end of the presentation. Our study improved the non-general bound on the parameter of optimal X code. So this shows the circuit testing with X code can achieve much more efficient compression than previously known without sacrificing test quality. However, there still remains a non-trivial gap between upper bound and lower bound. Another important thing is the weight of X code. So we are planning to address this point. Thank you for your attention.
Any questions? Okay,
I have one. So, I mean, the question is for both of you because maybe you know much better, but the flavor of what you did right here, t equals 1 would be over 3. But as the t increases, is this other property with the direct sum. Any relation to group testing for complex? So that would be a matrix in which the strength of what you want to locate, let's say, is bigger than 1. I mean, I'm sure it's not direct, but it seems this to be in between the two definitions. Yeah, so the group testing for complex is that you're not trying to locate one defective, but this might not be defective alone, not defective, but this interaction is defective. So a test that includes 2 ones will review a problem, but each one separately doesn't. There's a generalization that exists. So somehow the T1 becomes a bigger T in one of the sides. However, in the other, you're still keeping a 1, while in this other case, you would still wanting these two not cover any other pair, let's say. So there seems to be some relation. But I don't know.
Is it a special kind of locating?
I would say simpler, because locating arrays you have bigger alphabet. Here you still have the Boolean. Yeah, yeah. But it is relative to
There has to be some relation. And probably we can apply the same kind of technique, like this is just the relation method or explanation method she uses here. And she also used to say low pass flow lemma, and we are trying to apply some other cooperative methods. And as I mentioned, we also use graph lemma. So maybe we are not sure, but my impression is that it is very likely that we can apply some kind of technique to get similar results, because that's what we did here.
Any questions? Okay, let's thank all speakers in this morning.